at you. Speed of light and the shape of the universe. Kind of reminds you of Doctor Strange, doesn't you? Now, one of the greatest leaps and discoveries that happen in the world from physicists is actually using this technique from imagination. It's not actual physical things, it's more theory. And this technique is called, drumroll please, thought experiments. Now, Albert Einstein, one of the most famous physicists of all time, and the greatest physicist of his time, often performed these thought experiments, and this is why we even created the idea of general relativity. And one in particular had to do with light, and this happened in the 20th century, and it changed the way people thought about space-time itself. It made Einstein rethink the entire idea of the universe. So, now that the intro is over, let's start talking. So, his experiment, was a thought experiment, was like, can light move faster than light? And he was like, okay, let's think of the thought experiment. There's this train, and there's lightning that hit the front and the back. Now, to me, it seems I'm on the train station. It looks like it hit them at the same time. But a person inside, it looks like it happened at the front, then at the back. So, light cannot be faster than itself. So, the only thing that can change is space or time. Now let's just say that I can move about as fast as the speed of light for like about 10 minutes. Now to me it feels like 10 minutes, but to someone else, it'll be a little bit more than 10 minutes. Time and space are basically two parts of the universe. You can stretch them depending on your point of view and your perspective on the situation. Oh yeah, also depending on your speed. And can you even measure a muon? That's our next part. Now, muons are tiny particles. Now, they are smaller than atoms and are created when high-energy protons basically, like, smash into the Earth's atmosphere, and they're created from the sun. Now, muons actually rain down the atmosphere at not close to the speed of light. They travel so fast that we shouldn't be able to detect them. But we can, because of relativity. Now, muons should only exist for 2.2 microseconds. But after traveling about 2.2 microseconds, according to relativity, to us, it seems like it existed for 220 microseconds. And so, in 220 microseconds later, just before it disappears, it's low enough for muon detectors to detect. 1 billion IQ. Now, time travel. Now, the trouble with time travel, let's just say we have these two twins. One of them's an astronaut, one of them is like a guy like, I just gotta stay on the Earth. And so this guy, the astronaut twin is like, I'm gonna go on a space mission. I've been tasked with a space mission where I have to go in a spaceship and explore most of the universe that I can in 10 years. Now, the spaceship can go almost as fast as the speed of light. Now, her onboard clock, well, she speeds up faster than the ship, and it goes at 95% of the speed of light. And then to her, 10 years later, she came back. And to her, it seems like it's 10 years later. But to everyone else who was on Earth at the same time, 38 years have passed. Dun dun dun! And you look old. Yeah, I am old. And so now, no current spaceship can actually go at light speed. But later, when we can figure out how to go at light speed, this might be a big problem because we don't want to know that our younger brothers are now older than us. I just feel like in the blip, like, oh my gosh, my younger brother is now older than me. Now finally, we are E equals mc squared. E equals mc squared. E equals energy. M equals mass, and C is basically a code for light. So you can turn mass into, you can calculate how much mass is inside, how much energy is inside a certain amount of mass, and how much mass you need to create this amount of energy. In fact, 2 kilograms of just one piece of rock, can basically have enough energy, which is this many joules of energy. And that much joules of energy is how much joules of energy the United States of America currently uses in 1 year. So you can just use 2 kilograms of rock to power enough homes, and so that they can have like low cost electricity for a whole year. That is awesome. Now Einstein also said something else. If the whole universe is a stage, then gravity then the particles like the quarks and all those other things would be the actors, and gravity would be the stage, because people try to put in a particle called graviton to say this is what gravity works out, and it messed up their maths. Space-time is also a way you can curve the universe. Like if you put a bowling ball on the sheet, then that sheet is curved, and then if you basically put a marble next to it and the marble rolls, then it'll eventually get stuck in the sheet, and then it'll get attracted to the bowling ball. It didn't just get attracted. The bowling ball didn't just attract the marble. The marble itself actually just moved towards the bowling ball because the space-time was curved and it had nowhere else to go. And think of that in large scales with the sun, earth, and moon. Now do you see what I mean? Dun dun dun! So skip that. And that is it. You can spot space-time ripples, but it takes like 1.5 billion years, because the last space-time ripple, the closest space-time ripple happened 1.5 billion years, and light still hasn't appeared to us yet. So see you guys soon in the next episode. Next time we're talking about nuclear and particle physics. See you guys soon. Now, peace. Boo.